My name is David Rogers, and that is Sean Hill, and we are the co-founders of Earth Drones. Our topic today is using UAVs, photogrammetry, and GIS to extract and analyze environmental data, or put simply, using drones with cameras to create knowledge. Sean's been in conservation for 12 years, managing game reserves and volunteering his spare time in rehabilitation alongside FreeMe in SA. He's been employed by Virginia Tech in the US, and he's worked in Botswana in ecology, and he's worked in the agricultural sector in Australia. He returned to SA a couple of years ago and got his pilot's license. I'm a pilot with a fair bit of experience in the agricultural sector, flying ag drones in mountainous areas. I've also worked on wine farms in the Klein Karoo. We both decided to start Earth Drones to make a change in the Southern Cape, specifically in conservation. And we wanted to make a change not only for like the betterness of the planet, but just, you know, kind of spreading the knowledge of why drones will help, and why it's so much quicker than what it used to be. We've been working with SANParks, NISDA, and George municipalities, as well as the private sector, on environmental and agricultural monitoring, alien vegetation control, biodiversity rejuvenation, and management planning. We do our own in-house R&D with Nick Squared. That's Nick Swart, who's a master's student in soil science, and Nick Kutza, a student in GIS at NMMU. Unmanned aerial vehicles are certainly changing the game. I'm sure everyone can agree. There are various types of UAVs. You get multi-rotors, fixed wings, and a mix called vertical takeoff and landing, or VTOL. UAVs are versatile and can be used in tricky environments. Being accessible to almost everyone can help cover a much larger area a lot quicker than conventional monitoring methods, with higher accuracy and repeatability, which is very important. Red, green, blue, or RGB sensors on UAVs are cheaper to produce than multispectral or LiDAR, and we're going to be focusing on that in our presentation. So, photogrammetry is the science behind generating high-resolution digital models and maps using overlapped raw image data. So as the images overlap, you can kind of picture in your mind's eye how you would see a plant at an angle, and then as you fly over it, it kind of, you get height data from seeing the various angles using Pythagoras and all sorts of stuff. And then you can get a visual representation of how the overlapped images in the kind of focal area of the inspection zone are overlapped a lot more than the outside area. So expanding your map and getting a lot more overlapped images gives you a lot more accuracy. These images are processed using specialist software through a method called structure from motion. This is what it's all about. It relies on overlap data to generate geo-referenced orthomosaic maps, which are much higher resolution than the boundary of Google Maps, digital surface models, digital terrain models, and 3D point clouds and models. These maps are geo-referenced, which means they can be overlapped onto Google Maps, which is a reliable way of obtaining information. So what is GIS? Geographic Information Systems is an analytical computer system for capturing, storing, checking, and displaying data related to a position on the Earth's surface. GIS, in the GIS world, the real world can be broken up into various layers. These layers we can extract, and they contain specific data. For example, an agronomist would be able to use a soil layer to very good use, whereas the NSRI would use the floodplains layer for any sort of disaster management. One of the major types of GIS file formats is a raster file. Raster formats are used for their individual GIS data that vary, such as color, elevation, and GPS coordinates. Now that's raster, not raster. So using RGB sensors attached to UAVs to collect overlapped raw image data, processing this data through specialized software to create models and maps, then extracting and analyzing the environmental data with GIS to implement management planning is what we do. But why is it so accurate? Because of pixel size. Pixel size traditionally available for conservation monitoring have been way too large to accurately inspect details. Using satellite imagery, pixel sizes are generally 2 meters wide and on the ground, and could be months old and spoiled by cloud cover and all sorts of stuff. Where drones can quite easily achieve a 2 centimeter ground sampling distance, or GSD. This means that a 2 centimeter pixel is equivalent to 2 centimeters in the real world. That's 20,000 more pixels per satellite pixel. If satellites are telescopes, UAVs are microscopes. This is an example taken at 230 feet above ground level, using a front overlap of 80% and a side overlap of 75% for the raw image data to achieve this accurate orthomosaic in comparison to the 1 pixel represented there, 2 meters by 2 meters from satellite imagery. This is the edge of a geo-referenced orthomosaic. It's noticeable the difference between the Google Map resolution from satellite imagery and the Phantom 4 Pro V2 at the altitude. Gives us a chance to extract a lot more detailed information than was traditionally possible. Now remember looking really close at your parents' TV when you were young and seeing those individual little lights. Well, those are pixels, and they were red, green, and blue. And together they produce white light, or visible light, which is one part of the broader electromagnetic spectrum with wavelengths larger and shorter on either side. Our eyes can detect wavelengths of between 400 and 700 nanometers. With red, green, blue, when we start modeling, we can manipulate the color ramps. In other words, the pixels are assigned a number value to produce indices. RGB band values and various formulae are used to calculate the required index. Index data allows imagery obtained from relatively cheap UAVs compared to Dr. Sibanda's Matrice 300 with his Ultim, which is very close to what my car costs. This is a map of an area in wilderness. I will now show you how we can use these various indices pulled from RGB. Now notice the road at the bottom. That will be my representation of something that's non-living. So, to detect how much greenery is present and therefore detect plant stress, the formula is green minus red divided by green plus red plus blue. This produces the visible atmospheric resistance index, or VARI. Excess green emphasizes greenness of a leafy vegetation. You notice the bottom, it's not very leafy at all. Green leaf index is used to determine the impact grazing has on crops. If the value produced by the formula is negative, then it represents something that's non-living or soil. Triangulator or triangular green index is an indicator for chlorophyll sensitivity and provides insight into nitrogen levels in leaves of high leaf coverage. Sean will now get into some detail and explain how we've used these indices in projects from the past to extract useful data. Up here.
Thank you, David. Morning, everyone. Awesome to be here. Very cool. Okay, so it's David basically a lot of my yeah. Here we've got it's a pretty small transect. It's only 1.6 hectares. Pixel resolution of 1.1 centimeters per pixel. So we were looking at vegetation protection here, and also trying to get a little bit of a feel of what's going on with the adult and the So what we decided to do, if you're familiar with the quadratic vegetation monitoring system, put a grid around an area, and then you can do a lot of ground sampling in that particular block. So we did that over the entire area. So these are 10 by 10 meter georeference grids that you can then replicate in the real world and actually do your ground truthing through that. So if we take a closer look, you can see nice zoomed in little picture there of the aloes as well as bare soil and also some vegetation there. Now through the Hatari index, we can now start stripping data. So we can classify healthy vegetation to dry vegetation and separate soil values as well. So it looks something like this. So in this representation, the darker areas there are heavier green reflectance and the gray areas are slightly dry vegetation. White areas are then soil. And for a bit of fun, we tried to test ourselves a little bit further and actually detect some inflorescence data off the aloes themselves. So those purple sections there actually represent the reflectance from the inflorescence themselves. Okay, from that, we can then also use the digital surface model and the digital terrain models and actually gather height data as well in your Z-axis. So in this image here, the dark blues are closer to the ground, the lighter blues are higher up. So that gives you your Z-axis scale. Okay. So what sort of information can we gather from that? So as I said, the entire area is 1.6 hectares. The vegetation cover is around 55%. Which means that the vegetation covers around 9,000 square meters of that 16. Bare soil, looking at about 7,500. And then estimated volume of biomass is around just under 27,000 square meters, cubic meters, sorry. Okay, so we detected 315 living aloes. Of those, 107 were flowering, and there were 63 dead aloes within that transect as well. The average mean height of the entire transect in terms of vegetation cover was about 2.9 meters. The inflorescence side, and this is where it gets quite cool because it's, again, as Dave said, you know, we're looking at the world through a microscope in terms of this. So we could actually work out that the average size of the inflorescence is about 49 square centimeters. Ground truthing is quite accurate in terms of that as well. If you look at one of the grids, so this is particular grid is grid 40. So within that grid, 12 living plants. 5 of them are flowering, and there are other pieces of data there. The maximum height in that particular one is 3 meters. So we know that one of those plants is therefore 3 meters tall. And this is just a graphic representation of the entire area in terms of the heights data. Okay, so we take very alien vegetation quite seriously in the Southern Cape, where we're from, out in the wilderness area. This is the huge fires that we've had in the recent years are accelerated by alien vegetation. So in order to control them, we want to be able to understand what their age class is. Prior to putting in management planning and how to clear them. So we look at age classification, the density of the stands, the volume estimation of those stands, the native vegetation boundaries as well, pre and post removal monitoring to keep an idea of what's going on. We can then monitor the recovery of the area over time, and we'll get into that now. Okay, so this is the small transect of a sandrail property up in the Wilderness Heights area, which was cleared by Dr. Arne Witt of Cabby. They did a manual clearing of this area as you, of black wattle. So as you can see here, there's a lot of bare ground there. There's not much vegetation. So there's a lot of bare soil there. So once we use a process of delineation, we can then actually see quite clearly where there's a lot of bare soil and there's vegetation and the other interesting things. So all the data you will be seeing now is within this red area there. That's the target area that we were looking at specifically. Okay, this is 6 months later after clearing. You see a lot more vegetation coming into the picture. And when we do the delineations, you can clearly see that as well. Okay, now it gets a bit interesting. Okay, this is 14 months later after clearing. But now you can see that there's a huge amount of vegetation there. But there is, instead of soil, there's now dry grass because of the time of year that it is. So then that soil representation flips to dry vegetation. Okay, so that's what it looks like in a delineation. You can see that there's nice green reflectance there as well.
So just to have a look at some more data that we could pull out of that, we did a flowering chrysanthemoides or bitu count as well. So we know how many are flowering. We can also see there the newly established game trails that are coming through there. So to have a look at the vegetation cover mean that happened over this period of time, it was 24% of that area was covered in vegetation at the beginning, went up to about 60% in the summer of January 2021, and then up to 98% in September of 2021. So it's quite a drastic increase in vegetation cover. Now we get to the fun stuff. This is my favorite part of drone modeling. 3D point clouds, extremely useful stuff. We can get quite a lot of information out of these. Okay, so that's effectively what a point cloud looks like. You can see it's an image, tiny little dots make up that entire building. This is just a representation of the software that we're using. This is WebODM, a fantastic piece of open source software. And that's just the camera point. So that's just an illustration of how we can use, how you actually fly the drone to get a 3D model of a structure. In mapping, we obviously want to cover large areas. So this is a representation of a point cloud, but this has height data in it as well. So blue, obviously ground points, and then your high points of these trees represented in red. They've all got numerical data behind them as well. A 3D point cloud is effectively a 3D world with lots of points, each holding elevation data and red, green, and blue data as well. So if we look at our previous example of the Sanrail property, we can go back to that and look at that in a 3D point cloud. And we can then establish quite accurately what the average height of those plants are in September of 2021. So we're looking at about 3 meters there, highlighted in red of the tallest points, but the average seems to be around 1.5 meters. Okay, we can also then use the point clouds to have a look at erosion control beneath vegetation as well. This is a large area in the Watsonia stream area of wilderness as well. So if we have a look at the digital surface model, digital terrain model, you can see the red points illustrated in red, high points, and the low points in blue. So that's effectively with the trees removed. It's fairly accurate, but not as accurate as we would like it to be. So that's why we prefer to use a point cloud. I'll get into that in a second. There's 2 examples here of the strike slopes that we used. So we could actually do quite accurate measurements of what those slopes actually had, the slope percentage. So 22% for the first one and 31% for the second one. And that therefore equates to an 85% plus runoff for that area. Okay, because this area is all black wattle as well. So I forgot to mention that this is mostly black wattle and pine as well. So underneath that canopy, there is no native vegetation. There's nothing holding the soil back. So this is what a side profile of the 3D point cloud looks like. So with the vegetation indexes actually, or the elevation data for the vegetation in it. They're quite tall trees, well established. Quite tall. You can see there's some of those pine trees are sitting about 25 meters tall. We can then remove that from the digital point cloud, and then we've just got terrain data. And this is what you're going to be using to actually establish high levels of accuracy. So some of these areas that we've been looking at are quite small. Just to give you an illustration, obviously drones, we can do a lot larger scale stuff. So this is an area in the Bonnydale area. It's 90 hectares. To give you an idea of what that looks like, there's your height data and that's registered in there as well. This is also black wattle infestation. We were actually looking for somebody's cow, as a calving cow, but we didn't find her, unfortunately, but we got some awesome alien vegetation data in the catchments as well. There's a rugby field just to represent the size in terms of scale. So how do we control alien vegetation in rough terrain? The best way is obviously to use a drone. It's a lot faster as well. So using the initial photogrammetry information, we've then established the height class, the density, and all of the information that we need. We can then calibrate the drone to spray specific times of how to actually apply and what to apply. So I'm running over time here. So I'll just skip through it fairly quickly. So that's what it looks like afterwards. Quite little, very little collateral damage to the natural vegetation behind it. Okay, so reduction rate there is, we went from 60% cover, 61% cover down to 21% cover. That leaves a lot of barren soil, and then therefore we need to recover that, which we can do with drones as well. It's just a graphic representation of that too, in terms of reduction. Okay, point clouds also allow us to do change detection. So this is from a section of river in the Serpentine and Wilderness as well. From the middle of the year, that's from last week. If we then compute the distances between those points, we can also then look at growth and change in the environment as well. So we're looking at about a 90 centimeter change in the green highlighted areas. We upscale that to the whole area. We can then see what the change is over the entire river course. So comparing the old model to the new model, you can see where the Phragmites is actually encroaching into the river further, and it's grown a lot taller over that period too. So that's quite a nice representation of that. I'll hand back over to Devo.
Thank you, guys. We're running out of time, so I just want to mention there are a ton of other uses, including on the Serpentine River, just looking for illegal fishing and illegal netting, deforestation due to urbanization and agriculture. As mentioned earlier, we can measure whales, not as specifically, but we'd love to get into that. We'll talk about that. There's a ton of other uses that I'm not going to get into, but just lastly, RGB data combined with powerful software can consumer level and prosumer level drones are exceptional tools, and we're losing wildlife and wild spaces faster than ever before. With tech, we may have a chance of slowing biodiversity loss and environmental damage caused by humans.
What do we want to feel? What would satisfy us as being the meaning behind this world? It's very commonly said that the root of most human unhappiness is the sense that one's life has no meaning. It's so often, you know, that we don't follow our ideas and our desires through. Most of the things that we want very fervently are things that we've only half glimpsed. Our ideals are very often suggestions, hints, and we don't know really exactly what we mean when we think about it. But there is this obscure sense in which we feel that life ought to have significance. An individual feels that his life amounts to something when he belongs. He feels he belongs in a plan. And this too seems to give people a sense of great satisfaction. Why is it that a plan, why is it that fellowship with other people gives the sense of meaning? It does seem to me that there's a sense in which we often use the word significance, where the word seems to be chosen quite naturally, and yet at the same time it's not quite the right word. We say, for example, often of music, that we feel it to be significant, when just at the same time we don't mean that it expresses some particular kind of concretely realizable emotion, and certainly it's not imitating the noises of nature. It is felt to be significant, not because it means something other than itself, but because it is so satisfying as it is.
Okay, you good?